Hey everyone, welcome back to the channel. In the previous video, we saw a quick demo of our final Django app where both PyTorch and TensorFlow models make predictions side by side. Today, we're going to start building that app from scratch, beginning with the PyTorch model. In this video, we'll build a convolutional neural network, CNN, using PyTorch to classify images from the CIFAR-10 dataset, one of the most popular datasets for learning image classification. We'll train the model, evaluate its accuracy, and finally save it. So later, we can load it into our Django web app for real-time predictions. So let's get started. I'm already inside my virtual environment and running Jupyter Notebook, which I showed how to set up in one of my earlier videos. I'll leave the link to that video in the description. So if you haven't set up your virtual environment yet, make sure to check it out before continuing. Okay, here's what we'll do step by step. First, we will load and visualize the CIFAR-10 dataset. Then we will build a CNN from scratch using PyTorch. Then we will train and evaluate the model. And at the end, save the trained model so we can reuse it later in our Django app. By the end of this video, you'll have a fully trained PyTorch model ready for deployment. And in the next video, we'll do the same thing using TensorFlow to compare performance. Okay. So let's get started. We'll begin by importing the required libraries. We'll begin with importing the OS. It'll help us handle the file paths later when saving our trained model. Then we import Torch, the core PyTorch library. This gives us access to tensors, model training utilities, and GPU acceleration. Next, from Torch Vision, we import transforms. These are really useful for pre-processing and augmenting our images before feeding them to the model. We also import data loader from torch.utils.data. This will help us efficiently load our dataset in small batches during training. Then matplotlib.pyplot just to visualize some sample images from the dataset before we start training. And finally, we import torch.nn and torch.nn.functional, which we'll use to define the layers and activation functions in our neural network. So this sets up everything we need to get started with building our convolutional neural network. Okay. All right, now let's prepare our data set. The first thing I'm going to do is set a learning rate. I'll use 0.001, which works well for most CNNs trained on CIFAR-10. Okay. Okay. Here I'm using compose function to chain two important steps. First, the toTensor function. This function converts the images from PIL format into PyTorch tensors. And second, the normalize function. This scales the pixel values to the range from -1 to 1. Since CIFAR-10 is a 3-channel color dataset, I'm normalizing each channel using a mean and a standard deviation of 0.5. So normalization helps the model converge faster and makes training more stable. Okay. Before loading the dataset, let me quickly show you what our dataset actually is. The CIFAR-10 dataset consists of 60,000 images, each of size 32 by 32 pixels, divided into 10 different classes. There are 50,000 training images and 10,000 test images. And these are the 10 categories: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. Okay, now let's load the dataset in PyTorch. I'm using torchvision.datasets, a CIFAR-10 function, and I'm passing in three things: the root folder where the data will be stored, whether it's the training or testing split, and the transforms we defined earlier. Setting download equals true will automatically download the data if it's not already present. And finally, let's create our data loaders. Data loaders help us load the images in mini batches. Here I'm using a batch size of 32. For the training loader, I set shuffle true, so the data is mixed every epoch, which helps the model generalize better. For the test loader, shuffling isn't needed. Now let's run this block. Okay, looks like we've got an error here. Torch vision is not defined. Yep, we actually missed a couple of imports. Torch Vision is the package that contains popular datasets like CIFAR-10, as well as image transforms and pre-trained models. So we definitely need that imported. And next is Optim, which is a PyTorch's optimization library. We'll be using it later to define our optimizer. Okay, we have a typo here. Oh, we have another small issue. And there we go. 100% downloaded. So our dataset is now ready, and we can move on to the next step. These are the 10 categories in the CIFAR-10 dataset. The dataset internally stores class labels as numbers from 0 to 9. So having this list makes it easier for us to translate those numeric labels back into readable names when we visualize images or print predictions later. Before we start building our CNN, it's always a good idea to take a look at what our data actually looks like. So here I'm grabbing the very first image from the training dataset. This prints the type of the image, and you'll notice it's a PIL image before any transformations are applied. And the label here corresponds to one of our class names. For example, if the label is 6, that means the image is a frog. Right, so the problem here was actually pretty simple. We accidentally named our variable transforms, which clashes with the transforms module we imported from Torch Vision. So let's rename it to something safe. I'll call it transform instead. Next, I'm going to use matplotlib to show the image. So this line just sets the figure size, a wider aspect ratio, so the image looks nice and clear. Okay, I'm fetching the image again. This step is important because if we plot the normalized tensor directly, the image will look washed out or distorted. Since we normalized using x minus 0.5 divided by 0.5, we undo it by doing x times 0.5 plus 0.5, which restores the pixel values back to their original range. Okay. Matplotlib expects images in the shape height cross width cross channels, but PyTorch uses channels cross height cross width. So permute 120 rearranges the axis to match what Matplotlib needs. And this simply sets the title of the plot to the corresponding class name and then displays the image. Okay. Okay, we missed the closing bracket here. Oh, great. The output is finally showing up. You can see here that the image we extracted from the training set is displayed on the screen, and the label printed just above it says frog, which matches perfectly with the picture. Remember, our dataset doesn't give class names directly, it gives numeric labels. So when we printed classes label, it translated that numeric index into the human readable class name. In this case, frog. All right, now let's define our CNN architecture. I'm creating a class called SimpleCNN that inherits from nn.module, which is the base class for all neural network models in PyTorch. Inside the constructor, the first thing I do is call super, which just initializes the parent class properly. Okay. Now let's walk through the layers one by one. Here the input has 3 channels because our images are RGB. I'm generating 32 feature maps using a 3 by 3 kernel. The padding is set to 1 to make sure the output size stays the same as the input. Okay. Okay, now the second convolution. This takes the 32 feature maps from the previous layer and converts them into 64 deeper feature maps. Again, we're using a 3 by 3 kernel with padding, just like before. Okay. Okay, now the max pooling layer. This basically reduces the height and width of the feature maps by half. Since CIFAR-10 images are 32 by 32, applying 2 pooling operations will reduce them down to 8 by 8, right? So 32 divided by 2 equals 16 and 16 divided by 2 equals 8, okay? If you're new to these layers, make sure to watch our earlier CNN architecture video. The link is in the description, okay? Now comes the fully connected part of the network. After flattening, the number of input neurons becomes 64 cross 8 cross 8, which is 4096. This brings the features down to 128 neurons. Okay. And finally, the output layer. Since CIFAR-10 has 10 classes, this layer gives us the final prediction scores for each category. And at the end, I'm just storing a folder path /model where we'll save our trained model later on. Okay. Now let's define the forward pass, which tells PyTorch how data flows through our network. Inside the forward function, the input tensor x first goes through the first convolution layer, followed by an activation function, and then a max pooling operation. After this step, the spatial size goes from 32 by 32 down to 16 by 16, while the depth becomes 32. Next, the output goes through the second convolution layer, again followed by ReLU and max pooling. This reduces the spatial size even further from 16 cross 16 to 8 cross 8 and increases the depth to 64 feature maps. Okay. Now, once the convolution and pooling stages are done, we need to flatten the tensor so that it can be fed into a fully connected layer. So I use x equals torch dot flatten x comma 1. So this keeps the batch size as it is and flattens everything from dimension 1 onward. Okay. Then the data passes through the first fully connected layer with a ReLU activation, which gives us a 128 dimensional vector. And finally, it goes into the output layer, which is FC2. This produces the raw class scores for all 10 categories. We don't apply softmax here because cross entropy loss automatically takes care of that during training. And at the end, forward function returns the value of x. Okay, we have small correction here. And we have another issue here. Looks like an indentation issue. Now let's run this again. Okay, this looks good now. All right, now that our CNN model is defined, let's initialize it and set up everything we need for training. First, I'm creating an instance of the model using model equals simple CNN length of train dataset dot classes. Our dataset has 10 classes, so this will automatically configure our final layer with 10 output neurons. Okay. Next, the loss function as cross entropy loss, which is the standard choice for multi-class classification problems. Next, the optimizer. Here, I'm using Atom, which is widely used and generally performs well out of the box. I'm passing in the model's parameters and at our learning rate. Also, let's specify the device. For now, I'm using CPU. Later, when we compare PyTorch and TensorFlow, or when we deploy this inside Django, CPU mode will be perfectly fine. And we print it just to confirm. Okay? Let's define a variable that we'll eventually use to save the best performing model. Now, let's define the training loop, and we will be training for 20 epochs. Okay? Now, at the start of each episode, we will set the model to the training mode. Okay? We also initialize running loss to keep track of the total loss for that episode. Then we loop through the training data loader. And for each batch, we will grab the images and labels. Then we perform the usual PyTorch training steps. First, optimizer dot zero grad to clear previous gradients. Next, we pass the images to the model, which performs the forward pass. Okay. Then we will calculate the loss. Next, the loss.backward function is used to backpropagate the loss to the neural network. Optimizer dot step function to update the weights. Okay. We also add the batch loss to running loss. Okay. And finally, for each epoch, we print the average loss so we can see how the model is learning over time. Okay. All right, everything is set up. Our model, loss function, optimizer, and training loop are ready. Now let's go ahead and run this cell and start training the model. Okay, we have made a small mistake here. Let's fix the issue. Now let's run it again. Depending on your machine, this may take a little time, but once it's done, we'll have a trained PyTorch CNN model that we can later save and use inside our Django application. Great, our training is complete, and we can see the loss decreasing nicely over the 20 epochs. We started with a loss of around 1.29, which is pretty typical at the beginning. Then as the model kept learning, the loss consistently dropped down to about 0.06 by the final epoch. That's exactly what we want to see. The lower the loss, the better the model is fitting the training data. Now that our model is fully trained, let's evaluate how well it performs on the test dataset, which contains images the model has never seen before. First, I switch the model to evaluation mode using model.eval. This turns off layers like dropout or batch normalization updates, ensuring we get consistent results. Then let's initialize two variables, test loss to keep track of the total loss, and correct to count how many predictions the model gets right. Okay. Then we will use torch.noGradBlock, which tells PyTorch not to compute gradients during evaluation. Okay. And inside this block, we will loop through the test data loader, right? Now for each batch, we will pass the images through the model to get the outputs, okay? Then we will compute the loss and then use the torch.max function to get the predicted class for each image. Finally, we compare these predictions with the true labels and accumulate the number of correct predictions, okay? After the loop finishes, we will compute the average test loss and the overall accuracy, okay? Then we will print both values. This gives us a clear sense of how well our trained model is performing on unseen data, okay? All right, everything is set up. So let's go ahead and run this cell and evaluate our model on test dataset. Okay, we have a small issue here. Okay, now let's run it again. All right, the evaluation is completed. We got a test loss of about 2.15 and an accuracy of roughly 70.6% on the test set. That's actually a pretty reasonable result for a simple CNN trained on CPU without any data augmentation or advanced optimizations. Remember, this is a challenging dataset with 10 diverse object categories, and our model is fairly lightweight. Also, test accuracy is usually lower than training accuracy because the model is seeing these images for the first time. If we wanted to push this accuracy higher, we could add things like data augmentation, dropout, or train for more epochs, but for our purpose, this is perfect. We now have a trained PyTorch model that achieves over 70% accuracy, and in a moment, we'll save it so we can use it later inside our Django application and compare it with the TensorFlow version. Okay. Now that our model is trained and evaluated, the final step is to save it so we can reuse it later, especially when we build the Django app and when we compare the PyTorch version with TensorFlow. So we will use torch.save method and we will pass the model state and file name for the model. Here we will save it with the name model underscore CNN underscore PyTorch. Okay, let me quickly show you that our model file has actually been created in the working directory. This is the exact file we just saved using torch.save function, and this is the file we load later. Okay, all right. Before ending this video, I want to do one more quick test. I've copied a small folder here that contains a few sample images I downloaded from the internet. So this is an image of a frog. This is a picture of a ship, and so on. We're going to pass these images through our trained PyTorch model to see how well it performs on completely unseen real-world images, not from the CIFAR-10 dataset. Okay. Before we run predictions on the images I downloaded from the internet, I'm going to reload our trained model one more time, just to make sure we're using a clean, fresh instance. So here I'm creating a new simple CNN object with the same number of classes and then loading the weights from the file model underscore CNN underscore PyTorch. This ensures the model is in the exact trained state we saved earlier, and now it's ready to predict on our external test images. Okay. Now for this part, I'm just going to paste the code without explaining every single line again, because it's almost identical to what we did earlier with the CIFAR-10 images. Okay. The only difference here is that I'm loading an image from my external folder. This one is 2.jpg, resizing it to 32 by 32, applying the same normalization, and then passing it through our trained model. We then apply softmax to get the probabilities and print out the predicted class along with the confidence percentage. Now let's look at the image we are testing. And it's an image of a ship. Okay. So let me run this. And as you can see, the predicted label is ship and the model is extremely confident, around 99.97% probability. Now let's try another image. It's a large high resolution picture of a frog, actually the same frog image we used earlier in our CNN architecture video. I've put the link to that video in the description if you want to check it out. This image is much bigger than CIFAR-10, 32 by 32 images. So let's see how well our trained model can handle it after resizing and preprocessing. Now let's run this. Okay, we have an error here. Okay, image extension is incorrect. Let's fix it and run it again. And there you go. The model predicts frog with 100% confidence. So even though this was a large, high resolution image that we resized down to 32 by 32, the CNN was still able to capture the key features and classify it perfectly. This is a great example of how convolutional layers learn those universal patterns like textures, shapes, and edges that still hold up even when the input image is very different from the training resolution. All right, so that wraps up today's video. We trained a full CNN on the CIFAR-10 dataset using PyTorch, saved the model, loaded it back, and tested it on real-world images. And as you saw, the predictions were pretty solid. I'll leave the GitHub link with all the code in the description. So feel free to download it and try this out with your own images. And in the upcoming videos, we'll build the same image classification pipeline using TensorFlow. So you can see how both frameworks compare side by side. If you found this helpful, don't forget to like the video and subscribe. We'll see you guys in the next video. Bye bye.